This panel is going to be discussing post-quantum cryptography, PQC, also known as quantum-resistant cryptography, new maths-based cryptographic protocols designed to be proof against attack by a future quantum and conventional computers. PQC is also the leading branch of what's often called quantum-safe cryptography, which also includes the techniques from physics-based quantum cryptography, and which has been discussed in many other sessions in this great conference. I just wanted to go through that because these terms are sometimes used a little bit differently by different people. So first of all, let me ask each of our panelists to introduce themselves. First of all, Michael Redding.
Good afternoon, everyone, or good evening, or good morning, depending on which time zone you're in. I'm Mike Redding, and I'm the Chief Technology Officer at Quantropi, a Canada-based quantum security company, and happy to be here.
Dustin?
Hello, I am Dustin Moody from the National Institute of Standards and Technology, NIST. We're part of the Department of Commerce outside of DC. I'm the project lead for the NIST PostQuantum Cryptography project, which we'll talk about. And NIST does a lot of other research in many areas of science, many other experiments with quantum and so on that you're probably very familiar with.
Mike Osborne?
Hi, I'm the second Mike on the panel, Mike Osborne. I work at IBM Research in Zurich, Switzerland, where I head up foundational cryptography activities, including quantum safe, as well as kind of like pushing out implementations of the technology throughout our organization. So, hi everyone.
And Johann.
Hello everybody, good afternoon. I'm Johann Polecsak, CTO and co-founder of QANplatform. I've been a software engineer since I was 12 years old, and recently, since 2019, we've been working with blockchains and the post-quantum problem, how to migrate this kind of technology to utilize post-quantum cryptography. And Quan being the first and only blockchain on the planet, which is also Ethereum compatible, we will talk, or at least I will talk a bit about this proportion of the quantum problem.
Great. So let me lead us into the topic today. So quantum computers powerful enough to threaten our current encryption standards are still many years off. Mike, is this something that real IBM customers are actually worried about now?
Absolutely, and many of them worried since some time. I guess they really get that everything that we're not predicting today is potentially lost to a quantum future, and I think a lot of them are very aware of the difficulty in, let's say, migrating to becoming quantum safe. So many of them are still burnt by the memories of moving from RSA to elliptic curve cryptography, or from SHA-1 to SHA-2, and so a lot of them are very cognizant that it's in the past it's been a big cost, a big effort, taking a long time, and to be quite frank, a lot of our clients, a lot of people out there haven't even managed to migrate. So there are still large clients running things like DES, running things like SHA-1, just because how we've used cryptography in the past with the sort of low-level APIs that are typically used, it's just so very difficult to extract these from applications and move to something else. So people are really stuck with pre-OpenSSL version 1 API interfaces, and that's kind of like preventing them from actually taking advantage of, let's say, newer things. So they're really aware that agility, the ability to change crypto, is very, very important.
Dustin, when was it that NIST first took an interest in this? It's quite some time ago now. Can you briefly bring us up to date?
Yeah, so NIST has been aware of post-quantum crypto for a long time. Back in around 2010 or 11, some of our researchers wrote a survey report on kind of the state of the field. Back around 2016, we started to take some more concrete steps towards standardization. We held a workshop, we issued a report, and we also announced that we'd be holding this worldwide competition-like process like NIST has done in the past for some crypto algorithms like SHA-3 and AES. Since then, it's been a number of years. We've gone through 3 rounds of evaluation. We initially had close to 80 algorithms sent into us that were being evaluated, and each round whittled down the number where we selected the most promising ones to move on to the next round. Currently, we're at the end of the third round. We have 15 algorithms that are still in play. Of those, 7 are finalists and 8 are alternates. And very, very soon we will be announcing which are the algorithms which we will be standardizing first. That announcement's been delayed slightly from when I'd originally hoped. It still should be coming any day now. So.
Well, we wait with bated breath. And Michael, so Quantropi, you have a PQC offering, but you've chosen not to be part of the NIST process. You know, a lot of clients would think first about standard solutions. Why have you gone down a different path?
Well, first, I'd like to go on the record and say we wholeheartedly embrace the NIST process. I want that to be clear, and especially the philosophy of crypto agility. And so our flagship product, Keyspace, is a platform that provides a whole suite and series of cryptographic algorithms. And in particular, our mask asymmetric encryption suite will support the NIST standards when they're released. So if you want to announce anything, Dustin, this would be awesome. But once those come out, we'll, of course, we'll support them. But we also include novel PQCs that we've developed. They're from a known branch of cryptography around multivariate polynomial, but with some novel enhancements to make them truly quantum secure and overcome some of the issues of the past. And the reason they're not in the process was Quantropi was founded after NIST closed this current process. And so we hope to be in line if and when NIST opens up future considerations, say digital signature or potentially more candidates around key exchange. We'll be there and waiting. But in the meantime, we'll offer customers the right tool for the job. Let them have the choice, because in some cases, the NIST finalist will be what they've got to use because it's dead on the right capability. In other cases, especially around IoT, they may be looking for some alternatives that are perhaps lighter weight, have some different performance capabilities, and as a result, they can find the right tool to give them the post-quantum security they're seeking.
Johann, I know we had a panel earlier on this afternoon about blockchain and quantum safe, but what's your take on how blockchain is affected by the coming threat? Well,
it will be really critical. So when the only thing breaks which you can use to prove your identity, that being currently elliptic curve cryptography, you really can't do anything. I mean, anonymity or pseudonymity really backfires at this point, because there's no centralized entity. You just can't wave your ID that, hey, this is me, this wallet belongs to me, and please release your funds, please release my funds and let me migrate to a new PQC protected wallet. So there's no such thing you can do. And if you think about it, how this will go down is that there will be a series of steps. We will start by, well, acknowledging the problem. This has been already done, so this is the first step. Then you will see major blockchains like Ethereum starting hiring various post-quantum cryptography experts. This has also already been done as well. So I can show anyone job openings at the Ethereum Foundation for these roles. Then as the problem will approach, the next step will be that the leaders of these very well-known blockchains will go on stage and tell the public that it's really approaching and encourage everyone to please migrate their wallets to new post-quantum cryptography wallets. And even if we assume a 100% success rate, and by that I mean that everybody understands the problem, everybody is capable of doing such a migration, and everybody does it, it's still doomed, because if you look at it, how much cryptocurrency is in circulation, so how many so-called sleeper wallets there are, you just don't know whether the original owner even has the keys for them anymore. So even the legitimate owners might not be able to migrate their own funds. So, and in the end, you won't be able to make a difference between a legit owner migrating their own funds and an attacker cracking a wallet open and migrating to their own wallet. So it's a really hard problem, and it's really hard to solve. And even if we were given the task to that, please migrate Bitcoin or do something about it, we just couldn't. We just get lucky that we get to utilize post-quantum cryptography from block 0. So unfortunately, I don't have a solution for this either.
I'm conscious, Inside Quantum Technology, it's a great event because it covers such a wide range of these interrelated topics, but I'm conscious a good part of the audience probably doesn't normally look in too much detail at post-quantum cryptography. So I'd like to explore some of the basics. Johann, in discussion of PQC, lattice-based cryptographies really come to the fore. Why are people so excited about lattice-based methods?
Well, there are certain things. One is efficiency for sure. So if we look back when the AES was elected, so Rindal was selected, although it was a bit less secure than Serpent, for example, efficiency matters. And by that I mean that it will be a whole new phase. We can enable IoT devices to perform these cryptographic operations, and it's a huge difference. I mean, if we have architected various applications for blockchain, and there's a huge difference between running a blockchain node, which is telling some kind of information to a thermostat, for example, to set the temperature to 100 degrees Celsius and believing and doing that, or actually verifying that the instructions on the end device itself. So it's a huge difference in security. And also my personal favorite is homomorphic encryption, which, well, for blockchain, I mean, what we do, it's not such a huge difference because we can blindly trust any cloud provider because data is meant to be public by design. But for any other kind of workload, being able to outsource your compute workloads without having to trust that very organization who you are outsourcing to, I think that's also a game changer.
Mike, in talking about lattice-based crypto in PQC, we often hear talk about structured lattices. I mean, why is that a good thing? Why are we likely to see initial standards based on those rather than a full lattice?
So actually we use structures on many different forms of crypto, not just lattices, but they're used for two reasons. One is to improve efficiency in some dimension, whether that's performance or size or simplicity or something like that. The other thing actually to add characteristics like homomorphic properties. So that's why fully homomorphic encryption, ended up being solved on lattices because of the properties that you could add to via structures. So unstructured lattices or unstructured crypto, to get the security, it needs to be complex. So complex means things end up being large and slow. So that the other reason is you put things like rings in there, or what we call ideal lattices. These constructs that actually make the algorithms far more efficient, and that's where the efficiency comes from. So that's why lattice algorithms are now faster than what we currently use today. I do say that you have to be careful when you add structures. I think we're going to talk about Rainbow in a minute, but there were some early, I would say, clumsy attempts at adding structures to early lattice schemes that were broken. So you have this trade-off. You have to do these things very carefully, and very easy to make a mistake. But at the end of the day, you make these things practical, and practical in the sense that lattice, they're the nearest things we're going to have to drop-in replacements to what we use already. They are larger key sizes, but they are faster. But they're not that much larger key sizes that you can't use them everywhere. Other schemes, just because of the large dimensions of keys or things like this, very difficult to use in many scenarios. So really important for their practicability.
Dustin, just reflecting on the PQC, the NIST PQC process so far, IP patent considerations, they seem to have played a more prominent role in the process than many might have foreseen. Why is this area such an issue for cryptographers?
Well, cryptographers just don't seem to like patents. For the most part, in the history of cryptography, there have been algorithms that have been developed that can be freely used and are widely available and are strong and secure. And so why would you want to pay for an algorithm when you have a free one available that's been studied by experts? And that's historically been the way crypto has proceeded. In the post-quantum competition, there were some algorithms that have some IP attached. So that was kind of a more complex factor to play in. Algorithms that have patents tend to not be adopted as widely, and NIST very much wants the algorithms we select and standardize to be widely adopted around the world and implemented. So having a patent can slow that down. So it's something that we had to weigh in the factor of if any of these algorithms do have patents attached to them, how will that impact adoption? And our goal is to get strong cryptography widely adopted around the world.
Mm-hmm. So I think Mike already referred to something we saw just recently. One of the NIST PQC finalists was broken. The Rainbow digital signature algorithm was successfully attacked, and not by a quantum computer, but by a laptop running over a weekend. So Mike, how unexpected was the Rainbow break, and what should we learn from it?
For us, it wasn't, because it was our team that actually broke it. Apologies for that. I think there's a couple of lessons here. So the first thing to say, there's really a lot of discussion on the PQC mailing list about attacks and schemes being weakened and theoretical, let's say, constructs for very large machines in the future. This is not what the attack on Rainbow was. This was a very practical attack. And essentially the reason for it is that this need for optimization. So Rainbow has very large keys. So in order to make it widely useful, you need to do something to optimize it. Adding a lot of structure was the path taken. And as I mentioned, that's something you have to be very careful about. So in the end, it was actually a mistake in the way that the structures were added that was the cause of the problem. In terms of what to think and what to learn. I mean, at the end of the day, this is what I think is really great about this process, and that it has taught, or let's say focused, a lot of cryptographers on other people's algorithms, which is a very good thing. At the end of the day, in terms of the timing, I mean, algorithms can be broken at any time. I mean, they're not provably secure, so any such attack can come really from a quantum or a classical source at any time. So it's kind of how can I say, something you have to live with, which is why the agility is very important. And I have to say one thing which is also important, that the underlying mathematical hard problem, which is called an oil and vinegar problem on which Rainbow is based, is not broken. It's really just the optimization of it. And if there is a round 4 signature scheme, then we will also be very, very happy to contribute something based on that technology, but that maybe not quite so optimized, because it does have its merits.
Obviously, that attack was a conventional attack on the Rainbow structures. But Michael, do you think we've had sufficient, specifically quantum cryptanalysis on the NIST finalists?
Well, the old saying in cryptography is the best proof of the security of any algorithm is time, and also time is its greatest enemy, right? Because you're giving time for the attackers to come up. And I always use the analogy, children who are in college today, there's always been a Google, there's always been an internet, so their brains work differently. And in the next couple of years, there'll be children born who there's always been quantum computers. And so as a result, their brains will work differently, and they'll invent new attacks like we've never seen before. But so that's why a wide open, put it out on the table, let everybody see what's going on, let everybody take a shot at the title is the absolute only way to get to anything that has a chance to survive and to do what we need to do, which is protect the digital economy that the global economy is based on. And so that's why even though we're a small startup, our motto is bring it on, because whatever we're doing cryptographically, we're putting out there, because if you can't weather the storm, if you can't take on the challenges, either what we know or what we can only imagine, then we can't be secure.
So Dustin, we've already had a couple of the panelists talking about the round 4 in this process, and potentially call for new digital signatures. So what should we expect there?
Yeah, so the next few years, what you can see from NIST, like I said, the announcement of the primary algorithms that will be standardized first should be coming any day now. We also will have some algorithms that are advancing to a fourth round, and that's because when we selected the finalists, we picked the algorithms that would be ready at the end of the third round and would be ready to go and be standardized right then. Some of the algorithms we thought needed a little bit more time, and we also wanted to keep the focus on the algorithms we thought most promising during the third round. So during the fourth round, you'll continue to see more of these other algorithms being evaluated. Lattices were mentioned. Most of the finalists are lattices, but we don't want to put all our eggs in the lattice basket. So some of the other candidates are based on codes, based on multivariate, based on hash functions, based on isogenies. And so some of these algorithms will be in the fourth round for further evaluation and could be standardized at the end of the fourth round. With regard to signatures, at the end of the third round, we're seeing that we have a smaller number of signature algorithms that are still remaining in our secure. Rainbow was attacked, GEMS was another candidate that had some attacks. So we have a smaller number of digital signatures we're working with. We're very happy with the finalist lattice signature algorithms, but we also want to have a backup for them that's not based on lattices, that's a general purpose digital signature algorithm. So we are also going to have a call within probably about a year or so where we'll open up a smaller competition-like process, like we've done, to ask for more digital signatures that are general purpose, that are not based on structured lattices, so that we can complement what we select and have a diverse mathematical families to represent our post-quantum algorithms.
Yeah. So thanks. So defining these new cryptographic standards is one thing. But I guess implementing them and rolling them out over a large organization, that's going to be quite another, and that's a big piece of work. Mike, what should a large end-use organization be doing about this, other than calling their IBM account manager, of course?
Yeah, I think there's two things, okay? So there's certain things you can do as an organization, but there are certain things, if you play in an ecosystem, that ecosystem needs to do. So there are kind of a couple of dimensions. And I think there are two very other important points. One is the business case, or maybe it's kind of a requirement to sort of just migrate to quantum safe crypto would be a missed opportunity. There are other really very important cybersecurity efforts underway, things like zero trust, things like secure supply chain, that add easily as much cybersecurity benefit. So we would really recommend that organizations look at combining, not just looking at migration, but combining the move to something quantum safe with a more strategic aspect. So, for example, moving to zero trust technologies that are quantum safe, or supply chain, or fully homomorphic encryption, these sort of things. So to combine it with strategic elements that really get a much bigger bang for the buck than just concentrating on the crypto piece.
Yeah, Dustin, I believe NIST also has a migration to PQC project. How's that set to help?
Yeah, so NIST also has what's called the National Cybersecurity Center of Excellence that has a project to help out with organizations that are going to be migrating to post-quantum cryptography. They've partnered with the Department of Homeland Security in that. And the main goal is just to help put out good information for organizations to prepare and to get ready. There are other organizations that we heard about earlier today that are also issuing guidance. The NIST project, if you Google it, NIST post-quantum migration, you'll come upon it. Currently, they're gathering a community of stakeholders to work together and help work through some of the solutions that we can work out ahead of time without having to wait for the standards. So there will be reports, guidance, things like tools to help you find the crypto you're using that is vulnerable to attacks from a quantum computer. So just a lot of good resources there.
Johann, what should blockchain stakeholders be doing about this, other than moving to QAN?
Yeah, sure. So, well, generally speaking, there are quite some post-quantum cryptography power chains, so to say, but there are some things to watch out for. So I wouldn't pick a chain which is using purely post-quantum cryptography, so a hybrid should be in place. So I think we should rely on elliptic curve cryptography, like all the production blockchains are already running on it, and find an efficient solution how to combine the two to provide a safe migration path for the future. Again, I've also seen such things like using nested signature schemes where they try to nest one signature into another and resign it using a different algorithm. These are also useless from a point of, well, many points. Efficiency, storage space exhaustion, which is a very important topic for blockchains as the database is continuously growing. So, well, just avoid those. And also, well, this is a rather subjective, but introducing new APIs. So currently, 99% of the blockchain ecosystem as a whole is running on the Ethereum specification. So I would, and again, this is not just self-promotion, but generally market thing, that I would pick a solution which is compatible with 99% of the market. So I mean, the Ethereum specification already covers all possible use case scenarios a blockchain should have. So we should pick a solution which is compatible with that.
So, Michael, what customer segments are you targeting from Quantropi? What's a particular fit for customers that should look to you to help them along this journey?
You know, I think there's a couple different sectors. You know, of course I'll say everybody, but you gotta, you know, because who doesn't want their stuff to be secure? But a little more narrow, who's going to be the first mover, right? Who are going to make the first moves? Financial institutions, because that's where the money is. We saw, you know, the JP Morgan Chase example earlier today. So, you know, protecting your money and your money movement, heck yeah. You know, the carriers, right? Because that's the backbone of the internet. So all the previous sessions, you know, were all about core networks, because again, that's what makes the digital economy hum. So the carriers are on it for core networking. Automotive, I think it may have come up a little bit, but you know, securing the connected car is critical because it weighs 5,000 pounds and goes really fast. And so it's got to be safe. And that leaves one that actually a lot of folks don't talk about so much, but we see, you know, a real immediate market opportunity, and that's in medical devices, because it's literally life and death, and that can't be compromised. And so we were surprised. We thought that would be because it is a heavily regulated space, but what's regulated is the data integrity, and security is an absolute requirement for that. So actually, surprisingly, that's a fast mover, and a surprisingly fast mover with interest in post-quantum.
If I could just take it, just briefly touch on a related subject for a moment. I think one area that doesn't get a lot of discussion in the PQC setting is randomness and entropy. And I noticed that you know, IBM, Quantropi, QAN, you've all got offerings in this. Mike, how can IBM customers get their entropy post-quantum?
Yeah, it's an interesting question. So on the quantum side, we have the constructs like quantum networks, quantum startups. So there's been quite a few experiments run both using quantum computers, so circuit-based schemes, as well as, for example, now a cloud with external boxes. So evaluating kind of like what makes sense there. So if it's for experimentation, there are a number of avenues that we can point people to. I have to say that from our enterprise clients, then it's really the assurance is the number one thing. So having some form of FIPS 140 certification or common criteria certification. And there, I think maybe that's a question for Dustin, actually, to what extent QRNGs may be accounted for in the FIPS or the random number requirements for some of the assurance schemes. But so we already have these two things. The QRNGs are still very much on the experimental evaluation, and they will become, I guess, more production as and when the assurance schemes allow that.
Do you want to comment on that, Dustin, about where you might be with standards on that?
Well, I think NIST may move towards there. We don't have any active standardization of that at the moment, but we have things like the NIST random beacon that uses, quantum physics to generate randomness and is published online. So I think we're headed in that direction, even if we don't have something right now that we're actively doing.
Yeah. Michael, I see that Quantropi is secure, if I'm getting the part of your offering correct. You've got both QRNG and pseudo QRNG offerings. What are the merits of each?
Right. So with secure, we have quantum entropy as a service where we use hardware generated, FIPS certified hardware generation sources to create streams of quantum random numbers. In fact, we partner with Quintessence Labs as one of our supply partners on that key technology. And then we quantum securely transmit it over the internet as a service. So that's one modality. We then also have secure sync, which is digital quantum key distribution. So we can have an algorithmic approach to quantum key distribution and synchronization across multiple nodes for, again, many of the use cases we've seen all day today with our photonic QKD friends. And then last but not least, you talked about it, with pseudo quantum random number, sometimes you can't have hardware and sometimes you don't have a network connection. You need a low entropy device to be able to create sufficient quantum randomness, and we can do that algorithmically, ooh, say that 4 times fast, with our quantum permutation or keep technology. We can actually take that gold standard quantum random number from a FIPS certified source, but then do entropy expansion in software on the device to create random numbers with a periodicity of 10 to the 500th years, such that it can never be compromised, and as a result you can get it on literally any device anywhere. So streaming, synchronized, or locally generated, it all depends on, again, it's about crypto and agility, right tool for the right job.
David, can you close the session?
Right.
Okay,
So
you're at the end of the time.
Questions from the floor then?
We're at the end of the time.
Right. Okay. Well, thanks very much to all the panelists, and sorry for missing out on the questions at the end.
No worries.
Thank you.
Thank you so much.
Thank you very much
for a great discussion here.